Okay guys, let me greet you once more and welcome you to our next session or our next lecture. Today we are talking about heat. So we will basically focus on these topics, which are five. These are the five topics that we will look at: specific heat capacity, transfer of heat. In the transfer of heat, we will mostly be dealing with two basic with the conversion, with the law of the conservation of energy, heat value of fuels and efficiency, expansion, and finally steam. So that's what we'll be dealing with in today's section. Right, you can read through these definitions. Feel free to pause the video whilst you are reading through them. Make sure you understand them so that your job will be much easier. You can pause the video and read them. Okay, these are the advantages and disadvantages. Alright, I hope you did pause and took some notes. So let's move to the first question. These are the examples. Okay, this question reads like this: calculate the volume of water in liters required to cool 30 steel shafts. The initial temperature of the shafts are 800. The initial temperature is 800. That was supposed to be 800. The initial temperature of the shaft is 800 degrees Celsius, and that of the water is 25 degrees Celsius. The mass of each steel part is 200 grams. Let me quickly do something about this. Oh my goodness. I wonder what am I doing today. Yes, that's what I wanted to do. Okay, let's read the question once more. Calculate the volume of water in liters required to cool 30 steel shafts. The initial temperature of the shafts is 800 degrees Celsius, and that of the water is 25 degrees Celsius. The mass of each steel part is 200 grams. The final temperature of the mixture is 80 degrees centigrades. So we are asked to calculate that volume of water. So this is the formula. Actually, here we are jumping straight to the transfer of heat because we have two materials or substances. We have the steel on this side and we have water on the other side. So we need the volume of water that can cool this much of steel in terms of mass. So first things first, let's change that mass of steel into kg, because as we can see it is given in grams, and second we are told that they are 30. So each steel part or each steel shaft is 200. So we'll say 200 grams times 30 and find out what the temperature is. And find out what the mass is. And secondly, we have a lot of temperatures here. We have the temperature of the steel and the common temperature. We also have temperature of water and the common temperature. So let's see the formula to get the temperature right. This is the formula to calculate our temperature: the bigger value minus the smaller value. That's delta T. In other words, for the steel, it will be 800 minus 80. because this 800 is big, 80 is small. For water, it will be 80 minus 25. So that's what we will do for the temperatures. Specific heat capacity. There is information sheet in your question paper. You can just go on your question paper, look at the page, at the last page. You will see some information sheet where you will find C for steel and also C for water. C stands for specific heat capacity, so you'll find them there. So let me substitute for all of them. Let's do the substitution. Okay, this is C for what? For steel is 500, and this is C for water, which is 4187. Now the mass of steel, 200 times 30 is equal to 6 kg. So we just substituted in our formula to get the answer. But remember, the answer that we'll get here, it will be in kgs. So we need to change it to liters as we are doing here. So 9,38 kg is equal to 9,38 liters. That is the mass of water or the volume of water. So that's what we were asked to do, to calculate the volume of water. So this is the volume of water because it is in liters. Alright, let's go to the next example and see what is being asked. But before we do that, okay, then let's move on. I have prepared 2 exercises for you to work on during this time. After this example, I think you did understand something. So to prove that you have understood something, try out these 2 examples or these 2 problems. Thank you. Here is the second example. Water is heated from 18 degrees Celsius to 80 degrees Celsius within 1 hour. 13 kg fuel, 13 kg fuel with a heat value of 30 megajoules per kg is used. Take the specific heat capacity of water as 4,2 kilojoules per kg degrees Celsius. Now, when you are given the specific heat capacity, you do not need to go and read it on the formula sheet or on the information sheet because it's already given to you. So we'll use this one this time. Suppose that no heat energy is lost. Calculate the following, which is the temperature change, the heat energy given off by the fuel, the amount of water that is being heated. Alright, first things first, we need the temperature change. That's quite easy. I mean 80 minus 18, that will be the temperature change. So it's 62. Alright, then what about the heat energy that is given off? We have this formula for heat energy. This is Q. Q will be heat, so Q is equal to mF times HV. So mF means the mass of fuel times HV means the heat value. We do have the heat value there, and also we do have the mass of fuel because we are told that it's a 13 kg fuel that's being used. So we do have both of them, so we multiply them out to get our energy. Then the next thing that they want, it is the amount of water that is being heated, or that could be heated. So here they actually this example is okay. This particular question is similar to the previous one because they want the mass. That's the amount, the quantity of water. So we already got the heat energy, so we can substitute for the heat energy by its value. Specific heat capacity of water, substitute by it here. Change in temperature, we substitute by it so that we may get our mass. So this is the mass of this water. So I wrote it in liters as a volume. Otherwise, even in kg, if you wrote it in kg, you just have kg at the end. I have liters at the end because I just use volume. I just took that mass as a volume. That's about it. Let's move to the next question. The next question reads like this. Water is heated from 25 degrees Celsius to 75 degrees Celsius in 60 minutes by using 35 kg of a fuel with a heat value of 32 megajoules per kg. Now, for heat value, sometimes you might be given the heat value. Some of the times they may give you the name of the fuel. If they give you the name of the fuel, you can go to the information sheet to check what is that heat value for that particular fuel. So you can also do that. That is acceptable. So the question continues by saying the efficiency of the engine is 45%. Now we are required to calculate the change in temperature. Alright, the change in temperature is quite simple. 75 minus 25, that should give you 50. Alright, then we are also told to calculate the heat energy delivered by the fuel in 60 seconds. Also the volume of water that is heated. What do we have? These are the formulas that we are familiar with. Here I'm using E for energy, otherwise E is the same as Q. So we know this formula. We have another one. This is for power times time. Is still energy, is still work done, because work done and energy are quite the same. So this will be Q again, this E. Then energy out should equal energy out over energy in. That will give us the efficiency, because now we are given a new term, efficiency. This is the symbol for efficiency. Multiply by 100%. So what do we have here? Alright, for the first question it was easy. You just subtracted those two. Change in temperature, I can subtract them there. So the next one is heat energy delivered by the fuel in 60 minutes. So obviously heat energy delivered by fuel, because they're talking about the fuel. This is the formula we will use, because this is a formula that has the mass of the fuel, and we are given the mass of the fuel. We also have the heat value, so that means we have all the information needed to use this formula, but we will use Q in the place of E here. Yes, then since we are also told that this engine only delivers 45%, its efficiency is only 45%, so we have to include the efficiency to get the heat, because what we are also looking at is the volume, and they're saying the heat energy that is delivered. If we didn't put the efficiency, we will get the heat energy of the fuel. But now, because we have included our efficiency, that means we are saying this heat is being given, this is the one that reaches that water. So the heat that actually heats up this water is the one with the efficiency, and the answer for it is this one. So our Q is equaling 504 megajoules. So let's move to the volume of water. Again, we are using the same equation similar to the ones we used previously, but just now we included efficiency. That was a new thing that we were trying to show you can include in these formulas, efficiency. So you have the efficiency included, then we are able to find our volume of water. Okay, so the volume of water is 2407.452 liters. This is the volume of water in liters because the volume, so that is why we are using liters for it. Alright, that's about it. Thank you guys. Let's move to the next example. Okay, welcome again to the next example. Let me read this example. The steel block with a mass of 1,5 kg is placed in an electric oven with a capacity of 10.8 megajoules per hour. The temperature of the block rises from 25 degrees Celsius to 800 degrees Celsius. That's huge. The specific heat capacity of the block is 0.503 kg per kg. So this kg, or this kilojoule, if you were to look at the back, like at the back of the formula sheet, which is the information sheet, you'll find that on all of your specific heat capacity values, they are given in joules per kg. So that means this will be 503 joules per kg, but now they have this 0, something, so obviously they had to put that k, so that is why it is in kilojoules. So you should notice that value is given in kilojoules per kg. Okay, assume that only 68% of the heat reaches the block. Okay, you are told that there is an efficiency of 68%, and calculate time taken to rise the temperature of the block. Alright, we have this specific heat capacity, so it is given in kilojoules per kg degree Celsius. So we need to find the time taken to raise the temperature of the block. Alright, what's the information that we have? We are given the mass of the block. We are given what I can call, this could be energy per hour, which could be power. So I can say I'm given energy per hour here, which is basically the power. Now this power is the power of an oven, because that thing is placed in an oven with a capacity. So this is the power of the oven, or the energy per time of an oven. So we are also given, so this falls under the oven, so we are also given the temperatures of the block. Now they came back to the block, they gave us the temperature of the block, they also gave us a specific heat capacity of this block. After all that, they also gave us the efficiency of the stove this time. Now we are supposed to start our calculation. what do we have? We have P. Remember, I told you here that this is actually the power. So you'll write 10,8 megajoules. Mega is 10 times 6. Megajoule. Sorry. Let me say that again. This 10,8, you will say 10,8 times 10 raised by 6, because that is mega. Mega is 10 to the 6 divided by an hour. So an hour is 60 by 6, which is 3,600. So that value divided by 3,600, it will give you this amount. So that will be your power. I hope it makes sense. If it doesn't, you should play again. Then let's move to remember, what we want is the temperature. So since we want temperature, we know that we will come back to this formula, because this is the only formula that has temperature in this section. Okay, so we found the information, the power of the stove, but now we are looking for the temperature to raise that block. So that means the focus is on the block. This was for stove, then we'll use this for the block, but we still need that for the block before we can go to this equation. So this is why we are here, to find the Q for the block, the power, the work done for the block. So let's go. This is the mass of the block, which is given. This is the specific capacity is given. Change in temperature is given. Then finally we have the efficiency, because we need the Q of the block. So let's see, what do we get? This is what we end up getting. Then we take that, put it there, take the power, which is 3,000, put it there, to find our time. That's what we can do next. Time is equal to Q over P, obviously. We just made time the subject to the formula there, so we have it there. So our Q is this one, 397,600. What is it with me? So the energy that is received by the block is 397,625,5 in joules. So you substitute by that, you divide by the power, which is 3,000. You get your time. It will depend on you. If you want to calculate it in seconds, that will be the answer. Some people, they might want to change it to minutes. This will be the answer in minutes. Okay, let's move to the next example. We have this one. Let's read it. An engine has a brake power of 16.2 kilowatts. That is power, obviously. The engine is subjected to a brake test for 40 minutes. The mass of the fuel consumed is 2.25 kg, and the heat energy of the fuel is 32 megajoules per kg. Now we are asked to calculate the heat energy released by the fuel, number one. Number two, the equivalent power of this engine. And number three, it will be the efficiency of the engine. Alright, so let's move. They want us to get the heat energy first. What do we have? The mass of fuel consumed. That means we have the mass of the fuel. we have the heat value of this fuel. So if we have those two, we can get energy from them. Then we can use them to get our energy. Q, heat energy, substitute, and then we get our answer. Let's move to the next question. Let's move to the next question, the equivalent power of an engine. Obviously, this will be the formula for power, as we saw from the previous example. Then we have Q. I'm sorry guys, I'm not sure whether were you hearing me before, but I'm back again. Now we are asked to calculate the equivalent power of this engine. So this will be the formula that we'll use, as you've seen there. So we'll use the formula for power, which is this one. Okay, we substitute for Q, and we substitute for time as well, because we have 40 minutes. So we'll say 40 times 60, because we have 60 seconds for each minute. So 40 times 60 will give us the time in seconds. Then that will be our answer for power. Then we can move to the last question. Obviously this is bigger than that. Since it's bigger than that, that means this is the power in and that is the power out, because now we are going to calculate the efficiency. That is why we have to know. So we will just take the ratio of those powers, which is power out over power in times 100. So our efficiency will end up equaling 54%, because 16,2 divided by 30, that will give you 54 if you multiply by 100%. Right, chips, that's about it. Welcome to this example. We have this question. Let's read it. The size of a square copper plate. Okay, as you can see, when I say the size of a square, that means I have moved from the heat exchange part. Now I'm in another part where we'll be talking about the changes in area, or the area expansion. That means we are in the expansion zone. The size of a square copper plate are 150 millimeters at 127 degrees Celsius. The coefficient of linear expansion is 20 times 10 to the power negative 6. So this one is also one of the constants that are usually given in the information sheet if they give you the name of the plate. But this time they decided to tell you this coefficient of linear expansion. Otherwise they will give you, just go and read them. Alright? So the question says the temperature, it continues to say, the statement continues to say the temperature of the plate is decreased to 17, from 127 to 17 degrees Celsius. Now we are asked to calculate the coefficient of the area expansion. Now guys, when we need the area expansion, we just multiply this by 2. That's how to get the area expansion, as you can see. 2 times 20 will give you 40. Okay, so let's move to the next question. It says now we should calculate the final final area. Now the final area, this is the formula for the final area, is equal to the original area squared. So it will be if you have to change this to meters first, so it will be 0.15 times 0.15. That will be the original. Then what about the change in temperature? Now the change in temperature, it has a formula which says alright, you'll see it on the next line. Okay, we are back again. We have our final area equaling the original area minus the change in area. The original area, it will be that you just change it to meters. The delta A, that delta A equals to the original area times the coefficient of area expansion times the change in temperature. So that's the formula to use. Then you just plug it in there and then you get your final temperature. I'll give you the formula for this on the next example, because this coming example has exactly that formula, the one you want. Okay, let's get into it straight away. Let's read. An aluminium rectangular plate at 23 degrees Celsius with dimensions 25 centimeters by 10 centimeters is heated and the temperature increases to 65 degrees Celsius. Calculate the change in the area of the plate. Now we are given the measurements in centimeters. We need to first change them to meters, because you can see the answer is in meters squared. Obvious. That means we first start by changing them to meters. Then now can you see that formula was talking about? Here it is, by using it. So it's area times beta. Beta is equal to 2 alpha, which is that one, 2 alpha, times delta T. So delta T it will be the difference between those ones, because you see that is the temperature of the plate. Now the temperature has been increased to, it didn't say it is increased by, so it's increased to 65. So that is why 65 minus 23 will be our delta T. Now for this one, A is not given, but we are told that it's an aluminium rectangular plate. So we'll go to our formula, to our information sheet, look for the alpha of the aluminium, because the metal is written there. Coefficient of linear expansion of aluminium. You just read that value and substitute by it here. We have the original area, which is 0.25 times 0.1 there, because we have changed them to meters. How do you change centimeters to meters? You divide by 100. So 10 over 100, it will be 0.1. 25 over 100, it will be 0.25. That is why I was saying 0.25 times 0.1. Then you get your area. Then after that, you multiply everything out. This will be your answer. Okay. Then one more thing, I want to emphasize this formula to you so that you may see it better this time. Remember, when you're doing the previous levels and 2, you were introduced to change in temperature, change in length. So they said change in length is equal to original length times alpha times delta T. Now for area, it will be the change in area is equal to original area times 2 alpha times delta T. Or simply put, you can just say final length minus original length. For area to be final area minus original area, which is this one. So this is the formula we are basing this information from. Okay, so that's about it. Now I want to give you this exercise for you to try out. Thank you. Welcome back, guys. We have this question. This question reads like this: a fuel with a heat energy value of 42 megajoules per kg is used in an engine that develops 12 kilowatt during a test. The test lasts for 35 minutes and a thermal efficiency is 45%. Okay, or 45% is obtained. Calculate the equivalent power of the fuel, the heat energy dissipated by the fuel, the mass of the fuel. Without wasting any time, let us move on. This is the formula that we will need. So they are telling us that they need the equivalent power. Okay, from the previous example, we saw that the equivalent power from the previous examples, in fact, we notice that the equivalent power is the power input. So that means we are looking for the power input. We have efficiency, so we can put efficiency in its place. Now we will omit this 100. Okay, maybe let's not omit it, let's just go with it. Put 45% here. When this 100 crosses over, it will divide that 45%, and then percentage and percentage will cancel out. Then you'll be left with 0.45 is equal to 12 over pi. Then make pi a substitute formula, will divide by 0.45. Then your answer should be this one. This is the first answer. Let's move to the second question. The next question says calculate the heat energy dissipated by the fuel. So this is the formula for the heat energy. So we managed to get that value for heat energy. The next thing, it's the mass of the fuel. This is the formula that has the mass of the fuel. And remember, they already gave us the heat value, which is that one. So just calculated Q, we have the heat value, so we can just substitute and get the mass of the fuel, which is that as 1,333 kg. Alright, then let's move to the next example. Steam is generated at a pressure of 2. Okay, now the moment we talk about steam, that means we are in the section of steam, the last section in this module. Steam is generated at a pressure of 2,85 megapascals. Mega means 10 to the power 6. 2,85 megapascals to a dryness fraction of 0.96. Now dryness fraction is that X in that formula, in the formula sheet. The steam is now superheated to a temperature of 300 degrees centigrade. The specific heat capacity of the superheated steam is 2.9 kilojoules per kg degree Celsius. Now we are asked to calculate for 1 kg of steam, the amount of heat. What is this? Now we are asked to calculate for 1 kg of steam the amount of heat energy required for each of the following. The first one that they are talking about, is enthalpy in the wet steam. The enthalpy in the wet steam is number 1. So you have the formula in the formula sheet for this one. This is the one that has the formula. It's the only one. Then that is the answer if you just substitute everything to that formula. Now the next question says calculate the dry steam, which is Hg. Hg you just read to the steam tables. Don't have to do anything, just read to that steam table and get that answer. And they all told us for 1 kg, so you don't have to do anything, as the answer is say per kg, you leave it like that for each kg. Then they want the superheated steam. Now we do have this very beautiful formula for superheated steam. It says Hg, which is Hg, you got it from there. Then you will use the specific heat capacity of steam, which is this one, times the change in temperature. Now you go to this okay, let me start. When you were calculating this, you went to this pressure, you looked for the HF and the HFG. Then you substituted in that question, you substituted in that formula sheet, because X is given, which is the dryness fraction. Now that you want this one, you'll again go to this temperature and to this pressure, but this time you look for the temperature. The temperature, it will be your TS, the saturation temperature. So you'll have this 300 minus TS as the delta T. So you'll get that answer. Then you just add and multiply, subtract if you have subtract, and this will be the answer for everything. So our superheated steam is the answer for it. Thank you very much. Welcome back again to yet another inspiring lesson where we will learn a lot, but this time we will be talking about electricity. Alright, without wasting any time, let us begin. I want us to start straight from the circuits. We just have a little background, okay? Let me not do any background for that matter. Let me just go straight to the point. We have these two diagrams. Alright, obviously you know that's the resistor. That will be your voltmeter or whatever, galvanometer, whatever metering unit that is being used. We have a switch that is open. If the switch is open, that means there is no flow of current. Okay, it's supposed to flow in this direction from the positive to the negative. Okay, conventional flow, if it's a conventional flow. We have our cell here, maybe a battery, whatever it is. Now for a cell, this small line is negative, this bigger line is a positive. This E will be the one we will use for EMF, electromotive force. Then on this side we close our circuit. The moment we close it, now we have something. This E has changed into PD. PD standing for potential difference. Now why is that? It is because when it's open, when you measure between your poles, you'll notice that the amount of voltage reading you get for EMF is different from the one you are getting from the potential difference, even though you are measuring the same circuit. So the moment you close that switch, it drops. That is why we have that potential difference. It's the difference between the EMF and the voltage drop. Okay, then now everything is flowing, the current is flowing, the voltage is flowing through that resistor. So we are having a potential difference there. Let's go to the definitions quickly. These are the definitions for both of them. The electromotive force is EMF. I'll use E in this teaching of a cell. Is the voltage measured at the poles of the cell when no current flows through it. Of course, the switch is open. The potential difference of a cell is the voltage measured at the poles of a cell when current flows through it, or the difference in electric tension at the positive and negative pole of a cell. So that's what is called the potential difference. Let's go to other definitions. We have the ampere, which is the constant, which if maintained in two straight parallel conductors of infinite length of negligible cross-sectional area, or just cross-section, but the reason it's called negligible, this word negligible, it is because it is so small such that you can neglect it. That's what is meant by negligible. So that's the cross-sectional area of it, and placed apart in a vacuum will produce between these conductors a force equal to this amount of length per meter of length of Newton per meter of length. Yeah, so we move to Faraday's first law of electrolysis. The mass of a substance released or deposited during electrolysis is proportional to the current flowing through this solution. This is the formula for it. Then the second law of electrolysis says the EMF of different substances liberated by a given quantity of electricity is proportional to the chemical equivalent mass. And also for this one we do have this formula for it. Okay, we have a lot of things we need to talk about. We have that M obviously is M, that stands for the mass. Then we have I hasn't changed. I is always the flow of current, is the current flow. We have Z, which is the electrochemical equivalent. Then we have T obviously it should be the time that is taken. So here we just have M and Z, M being the mass and Z being the electrochemical equivalent. So that electrochemical equivalent is measured in grams per coulomb. Now the mass in these problems or in these particular formulas is measured in grams. That is why the Z is in grams per coulomb. Let's move to Joule's law. It states that It is the heat developed when an electric current passes through a conductor is proportional to the resistance, the time, and the square of the current. That is Joule's law. Alright, now we have this part. Now we are starting to talk about formulas. We are done with definitions. Let's go to formulas. We are starting by these two circuits. Connections in series of this circuit, connections in parallel for this particular circuit. Then let's see what they say. We have V, which is just the voltage reading. It could be EMF, it could be voltage drop, it could be potential difference, whatever it is. So it will depend on the circuit. If it's open, it will be EMF. If it's closed, it will be potential difference. So, or maybe it could also be the voltage drop, but we'll talk about the voltage drop later on. So this is our V, the voltage. We have RS. Now this RS, it is for the series, like the connection in series is for the resistors that are connected in series. As you can see, these ones are connected in series. Then we have I. This is I. Okay, for this one, I is constant. V, when the connection is in series, the voltages will be added up, then the resistors will also be added up and form that resistors for series connection. Whereas I is the same. When we go to the parallel circuit connection, we have our current flows being added up. We also have our resistors being added up, but this time we are adding them as reciprocals. So we will have the 1 over resistors for parallel connection, which equals 1 over R1 plus 1 over R2 plus 1 over R3. Or you can simply put it in this way. Put all of them under those brackets and you say to the power -1, because this is the reciprocal now. Okay, there it was 1 over RP. This time it's just RP, so that is why we have -1 there, because we actually flip this thing around. Okay, so this RP, let me tell you again, this RP is for resistors that are connected in parallel. Let's move to the next one. Here we have our E. So E, we say that E is actually EMF, but I will just use E. So it's the electromotive force of our cell or battery. So it will equal to the number of those cells and the volts of each cell. So for example, there we have 1, 2, 3. That means we will have 3 times volt for each cell. Or you can just say it will be the current that flows times RT is the total resistance. So it will be the total. When I say total, I mean RP plus RS. So it will be the total resistance that is in that circuit. If the circuit has both RP and RS, you add them. If it's only for RS, that means this RT will be this RS. If it's only the parallel connection, that means this RT will be the RP. So this RT is just the total resistors that are in that circuit, all of them. If it's a combination, all of them, both RS and RP will give you RT. Then we have RB. RB is the resistance of the battery. That means you have to add the internal resistance of those cells together to get the RB. So RB is the resistance of those of the battery, internal resistance of the battery. Then we have the potential difference. Potential difference could equal to I times RT. This time we will not include the RB, so we'll get the potential difference. Or we can just say we'll just say electromotive force minus I times RB, not times this one. So it will be I times RB. If we subtract that from electromotive force or EMF, we will get potential difference. That's how we can get potential difference. Okay, let's move further. Now let's talk about this RB. If your connection is in parallel, then your RB will equal the number of cells divided by your internal resistance. If your connection is in series, maybe for this circuit, like when I'm talking about series, I'm not actually referring to the circuit per se, rather than the cells. If the cells themselves are connected in series, then your total internal resistance of the battery will equal to the number of cells times their internal resistance for each cell. So that's how you get that RB. So RB, in other words, is the total number is the total internal resistance of the battery. Small letter r is the internal resistance of each cell. Then N is the number of cells that are there. Okay, welcome me back. So we are back again. This is what we ended up on. Let's move further. Now we are moving to V is equal to IR. Okay, this is the very famous formula. This is Ohm's law. So this is the famous formula. We all ought to know it. V is the voltage reading, I is the current flow, R is the resistance in that circuit. Alright, then let's move further to the total resistance. Now there's a difference between this total resistance and this one. This total resistance is the resistance for all that are there. In other words, if I wanted, I could have just substituted this by this resistance, by this total resistance, because this total resistance of the circuit plus the total internal resistance of the battery, when you add them up, they'll give you the total resistance in that circuit. Alright, both internal and external. So this is that total resistance. Alright, then obviously RT, the small letter t, is equal to RP plus RS. Then RB is the one for the battery, which could be this or that, depending on the connection of the cells. So that's about it. I am again explaining this RT there, making sure that you really know the difference. I already explained this one when I was talking about the Faraday's laws, both of them. This is the first law, this is the second law. Then let's move further to power and work done, or energy. This is the formula for energy. Q is always energy, as you've seen from heat as well. We used Q, but this time this Q is the electrical energy. We have I, which is the current. We have RT, which is the total resistance. Then we have T, which is the time taken. So we have V, which is the voltage reading. I and T and Q, you already know them. Then we move to power. For power, we have again I, which you know, R, which you know. Remember, power, if the formula for power, the one that is well known, power is equal to work done over time, or energy over time. So in other words, if we divide this energy by time, then we get this one. Same thing again here. If we divide this energy by time, we will get that equation. So that is the equation for power, is energy over time. Then we take this formula, we use it for transformers. So it's the same formula for power, but now we just use it for primary windings and for secondary windings. So that is the formula that we will use for transformers as the one for power. So we can also derive this formula from that power formula. Okay, where Vp is the voltage, the primary voltage, Vs secondary voltage, Np. Alright, you remember when I was talking about VIP, I said that it is the power for primary windings. So this is the number of turns, or the primary winding number. So those number of turns in that winding are known as Np for the primary side. Ns, again, it will be the number of turns of that copper wire around the core on the secondary side. Then we have Is. I again hasn't changed. I is current flow, but it will be the secondary current. Then Ip, it will be the primary current. Alright, that's about it. Okay, before I almost forgotten this, let me quickly add it. Then there is something that is called the voltage drop. So voltage drop equals to the EMF minus potential difference, or single I times RB. So if you take the current and multiply it by the sum of the internal resistance of the battery, you will get your voltage drop. So is that difference we're talking about when we were opening? Is that, we remember when we saw those two circuits on our first slide? So we said that the other one is for EMF and the other one is for potential difference. I said the difference between those two is called the voltage drop. So this is what we are referring to. And then finally, we can also talk about this thing. This will be internal resistance, but this time of an ammeter. So the internal resistance of an ammeter, I will denote it by that RA small letter. We know this, we know that already. Okay, so what do we have? We have this question as an example. 4 cells, each having an EMF of 1.5 volts and an internal resistance of 0.5 ohms, are connected in series. Okay, this is the connection of cells, not of the circuit. Two resistors of 6 ohms and 8 ohms respectively are connected in parallel. Can you see the difference? The connection of the cell is in series, the connection of the circuit is in parallel, and then across the terminal of the battery. Now we should calculate the current through each cell, the terminal voltage of the battery. We also need to calculate the current through each resistor, and finally the internal voltage. So what can we do? We go straight to that list of formulas. We select the one that will help us. Well, this is the one that I saw, because we need I, current is I, so we need I through each cell. Then we do have, or we can get the E, because it will be 4 times 1.5. We can get RT, our RT, because a parallel connection, it will equal to RP. Can get RB. We are told that the internal resistance is this one. So, and the cells are 4, so we can just multiply that by 2. And then we can get our I. So let's see that what did I mean. This is what I was meaning. E N times V, RP, RT is actually RP. Okay, then when we substitute by all of them, we just make I the subject of the formula, and this will be your answer. Let's move to the second question. They want the terminal voltage of the battery, so that is potential difference, which is this one. Okay, we do have I, we do have RT. We can just substitute by those, get the answer, and with this answer. Even if we just use E, because we have E, we have I, we have RB, we can still get it that way. So both ways will give us the same answer. Then let's move to the next question. It says the current through each resistor. This is resistor number 1. That's the formula for the first resistor. So this is the current. So you just divide V1 and R1 to get the current. You do the same for the second current. Alright, then finally the internal voltage drop. So that's the voltage drop. Just use that formula, because we have E, we have potential difference. That's the voltage drop, and that's it. Let's move to the next question. This is the next question, and it reads like this. An electric circuit consists of 3 cells connected in series, each having an EMF of 4 volts and an internal resistance of 0.15 ohms connected in series with a lamp with a resistance of 9 ohms. Calculate the total EMF of the battery, the total internal resistance of the battery, the total resistance of the circuit, the current flow in the circuit, and finally the potential difference of that battery. This is the formula for the first question, the EMF, simple, straightforward. You just multiply the volts for each cell by the number of cells. We are told that cells are 3, each volt has. If each cell has 4 volts, multiply 4 by 3, you get 12. Total internal resistance of the battery. Obviously, you know the total internal resistance is RB, capital letter R. So this will be your internal resistance. So that is what we have, and we are told that the connection is in series. That is why we are using this series formula, because they were very straightforward. The connection of the cells is in series, as well as the connection of the circuit. So both the circuit and the cells are connected in series in this particular example. Then the total resistance in the circuit, we are using the series equation or formula because they are connected in series. The circuit is connected in series, so we are having those are connected in series. In other words, this will be your RS. Okay, that's about it. As you can see, we have RT, which is this one, plus RB, which is this one. So that will give you that. Okay, we have now come to the current flow. We need to calculate the current flow. We are using the same formula we used on the previous example. We do have E12, we do have RT9, we do have RB 0.45, we do have I. Okay, we actually looking for I, but we have every other thing, so we just make I the subject of the formula and we substitute, and then we can press our calculator. This is an answer for our I. Then we have the potential difference of the battery. The potential difference, we do have the formula for potential difference is IR, or just E minus IRP. Whichever one you use, you will get the same answer. So that is it about this example. The next example is also similar to this one. Let's get straight into it. It says an electrical circuit consists of a battery with 2 cells, each with an EMF of 12 volts and the internal resistance of 0.4 ohms connected in parallel. What's connected in parallel? It's the cells. They are connected in parallel. Okay, let's move on. An ammeter with an internal resistance of 0.15. Now we have an internal resistance of an ammeter. Remember when we talk about ammeter, the resistance of an ammeter? So this is it. The internal resistance of that reader, which is an ammeter, is connected in series with, can you see? It says with. Now we're talking about the resistance. We have resistor A of 2A and the resistor B, which is 4 ohms. Now we are asked to calculate the total internal resistance of the battery. Remember, we have 2 cells, and those cells are connected in parallel, so that will mean our RB, this is RB, the total internal resistance is RB, so our RB will equal to internal resistance of each cell divided by the number of cells, so it will be 0.4 divided by 2, and the answer will be 0.2 ohms. Does it make sense? I hope it does. Then we move to the ammeter reading. Remember, we have this for ammeter as well, okay? So let's see what are we going to have. Ammeter reading, this is the formula that we can start with, but what is RT? Our RT in this case will equal to RA, which is that the internal resistance of the ammeter. Remember, it's connected in series with these two resistors. So in other words, we will add both of them in series. So we have 2 plus 4 plus 0.15. That will be our RT. Then we again add RB, which is 0.2. So that will be the answer for this bracket. And then we just find our I. Okay, remember EMF for a parallel connection of the cells is 12. So EMF is 12 here. Thank you very much. Now I think we are done with this section. Let's move to other examples, or let's move to another section of this module. Thank you very much. Let me welcome you once again to another exciting section. We have this example. We are told that the following appliances are used for a given period of time per day. Number 1, 10 60-watt lamps 4 hours per day, 5 100 lamps 6 hours a day, 1 2000-watt stove 1 hour per day, 2 computers using 75 watts 3 hours a day. Then we are told that the electricity cost 163 cents per kilowatt hour. We are asked to calculate. We are asked to calculate the electricity cost for 7 days. What can we do? Obviously, we will start with the first one. Since I can see that is the first one, that I want to make it I want to put it in an orderly format, so I'll start with the first one. So 10 times 60 for the day, that means times 4. Then you divide by 1000 because we need it in kilowatt hour. So let's divide by 1000. So we get it that way. Then let's move to the second one. 5 times 100 times 6 hours a day divided by 1000 as well. That's the answer. Let's move to the third one. 2000 watts times 1 divided by 1000. Then let's go to the final one. 2 times 25 times 3 hours divided by 1000. So this is what we have. Then let's add all of the above to get this for each day. Remember, we are asked to find it for 7 days. But now for each day we have this. Let's multiply it by 7. Okay. Now we have, let's get the answer for 7, but remember, we also have the cost. So this is the answer for these 7 days. Then now the question was saying calculate the electricity cost, so we should include the money, amahaheba, shelete, mula, inyuku, fetu. So let's talk about money as well. Multiply by money there by our 163 cents, and then we end up getting almost 100 rand. It's 89 rand and cents. So that will actually be the cost of this electricity for this particular week. Yes. Okay, let's move a little further to the next part of our examples. Now I think we are going to... Alright, so we are told that a learner conducted an experiment, I think it's Faraday. A learner conducted an experiment in a laboratory using an electric current of 100 amps. The experiment was done for 2 hours through a solution of copper sulfate using a copper anode. The electrochemical equivalent of copper is 3,294 times 10 to the power -4 grams per coulomb. So this is electrochemical equivalent value. Now they are asking us to calculate the mass of copper that is being deposited. Okay, let's take down the data. We have our I being 100. We have our T time being 2 hours. Remember, each hour is equal to 60 minutes times 60 seconds. Now we multiply it by 2 because it's 2 hours to get the 72,000 in seconds. Then we also have our electrochemical equivalent. Alright, then let's move on to our formula. Now this is the formula that we have. We can just substitute by it because we need the mass, and this one was not hard at all because even the formula itself is given in this format. So we just substituted by everything so that we may get the mass in grams, because our mass is calculated in grams for this part of the section. This is yet another example for us that we need to go through. An electric lamp is marked 230 volts, which is 200 watts. Calculate the cost to operate the lamp over 3 hours at a cost of 25 cents per unit. You have two ways of calculating this. You can use either the one on the left hand side or the one on the right hand side. It will depend on you, even though I prefer this one, but you can use anyone you think is more understandable for you. So you substitute for power because it's watts, that is power, and then you have 3 hours in time. Then for this one it's megajoules, for this one it's kilowatt hour. So we need the cost, so you just divide the kilowatt hour by kilowatt hour and multiply by the amount. On this side you divide the answer by... Now where does this come from? Remember, 60 times 60 is 3,600. Now we always use this one as 3.6 megajoules to divide whatever way you included the 60 times 60 value for the time. So in total this will be the final cost, because it was not yet an hour. It didn't reach 1 hour. I mean, it didn't reach 1 kilowatt. So this was the answer for it. Okay, let's move. Maybe it's my final example, I'm not sure. Let's move to another example. We are told that an electric bulb is marked 220 volts. Oh no, it's not the last example. There is another one. I think two more that are coming. An electric bulb is marked An electric bulb is marked to 20 volts, 80 watts. So this is voltage, that is the watt. An ammeter in the circuit shows that the bulb uses 0.3 amps. Then now we are asked to, okay, so we're also told that the bulb burns for 1 hour. Let's calculate the electrical energy that is being consumed and also the cost of the bulb to burn. For 1 hour, if the cost of electricity is 26 cents per kilowatt per hour. Okay, so this is what we have for the first question. Electrical energy, this is electrical energy. I is given, V is given, T, where is T? 1 hour, T is given. So everything is given. So 1 hour is 3600 seconds. Then you just multiply and you get your answer. Then the second question, the cost. Now we are looking for the cost. We already have our energy. So now we will just divide it by 1000, multiply it by 1 hour. Then we have that answer. Then again we multiply by our 26 cents to get the final answer. So this is how we will get our answer in this section of questions. Okay, let's do another example, guys. Welcome back. Let's read this example. A single-phase transformer has a supply voltage of 240 volts, so that and a primary current of 6 amps at full load. The secondary current is 0.4 amps and there are 600 turns on the primary coil. Now we are asked to calculate the number of turns on the secondary coil. We have 600 in the primary. We need for the secondary. Secondly, we need the secondary voltage because the supply voltage is the primary. Secondary power. So power is equal to VI. So we'll just use the secondary side of that power. Okay, for the first one, the number of turns, that is the formula we can use for the number of turns because we have 2 amps. We have the number of turns of the primary coil, so we only need the number of turns for the secondary. Otherwise, every other thing is there. So that's the answer. Then let's move to the second question. Secondary voltage. Secondary voltage. We are looking for it. We have the primary voltage there. we have the number of turns for both primary and secondary. We need only the voltage, so we can use this one to get the answer. In fact, if you wanted, you could also use this, the volts and currents as well. It was supposed to give you the same answer. Then finally, we are asked to calculate the secondary power. As told you that formula for power is VI. So this is the power for the secondary side of our transformer, and that will be the answer, 1,4 kilowatts. So this will be the answer for this question. Let's move to yet another question for us. We have that statement, and then we are asked to calculate these. Okay, let's read the question. I think this is the final question for it. Determine the power rating of a stove if it releases 200 kilojoules of heat energy in 4 minutes and 30 seconds. So this is the time, 4 minutes 30 seconds. This is the amount of energy. So that's energy, that's time. Then let's see, what do we have as they are asking us to find the power. So what's the formula for power? Obviously power is energy over time. So we'll just divide these two. We just need to change this into seconds only, not minutes and seconds. Let's quickly change it, multiply it by 60, then we add the seconds, so we have 270 seconds in total. We already have our energy here in kilos. So kilo means 1000, so those 3 zeros are from kilojoules. Then we have joules. So let's divide those two, and that is the answer. Ladies and gentlemen, that's how much I had in store for you today. I hope you are doing great and you are enjoying. See you next time.